Here goes. What's going on, guys? I want to do a quick follow-up video to the trim solenoid video I just put out. This is going to look like some kind of weird sort of concoction here, but let me explain what's going on. So, in the last video I explained how the solenoid works, and if you remember, there's that coil of wire. I can get my drawing out, but whatever. So there's a coil of wire in there that activates this magnetic solenoid. So I actually thought it'd be kind of cool to take one of my old solenoids. I bought two new ones, and I basically fixed the two old ones. I got them both actually in working order. So I had two. I was going to keep them as backups. I'm going to keep this one as a backup because I can always use this for the starter if I need to in a pinch. But the other one I thought it'd be cool too. I actually took it apart and ran it through my bandsaw, so I was able to actually get a cross section of it. You can actually see inside here now. This is the coil, the magnetic coil, the disc, and then the two copper studs on top that I had cleaned up. And what I have set up here is a little experiment I wanted to run. So when I took these things apart last time, this disc and these two studs were just totally, and you can still see it on the side of this, they were just totally covered in carbon. They were real nasty, black, all pitted. They were in not the best of shape. And one thing I realized was a lot of the pitting is being caused by arcing, and it's kind of the same process as like EDM machining. If you guys know what that is, it's electrical discharge machining, which is basically you use electrical current to actually remove metal. It's actually a pretty cool process. You can check it out on YouTube or Wikipedia or whatever if you want to learn more about it. But that's essentially what's going on inside of here. There's electrical current, and when it sparks, it's actually eroding the metal, which is what causes those pits. So what I wanted to do is actually try a little experiment here with this cross section. What I have here is it's actually an 18 volt DeWalt drill battery, because it's capable of delivering a good bit of current. So what I have is one terminal going down to the solenoid, and then the other terminal coming over here, and then the other terminal, the battery, going to the plug. And it's going to look a little sketchy, but I have it basically plugged onto what appears to be an AC plug, which it is, which is going down to this centrifugal water pump I have. I'm not afraid to run this for a few seconds without any water in it because it's a centrifugal pump, so it's okay to run dry for a little bit. But the key here is this is an induction, or a universal motor. So it's actually got brushes in it, and it'll run on either AC or DC. The reason I'm not using my trim pump motor now that I have that rebuilt is because if I run that without oil in it, you can run the risk of damaging the actual hydraulic unit itself because it relies on oil for lubrication. That, and if I started it up, it'd spew whatever oil's in there out all over my basement, which I don't want to do. So figured this would make a good substitute. It's a decent size inductive load, which that is as well. So what I want to do here is I'll set the camera up, and what I'm going to do is same thing I did in the other video. I'm going to touch this to activate the coil. What I'm going to look for is sparking in here whenever I disconnect the coil. And what happens is when you put power through a coil, the current, the coil tries to resist a change in current. So when you first start it up, the current will actually kind of slowly ramp up until the coil is fully saturated, and then it almost acts like there's nothing there. So when you first turn on a circuit, it sees a coil as an open circuit until it's saturated, and then once it's saturated, it sees it as a short circuit. So then you kind of max out, and then the key here is when you actually disconnect the coil or break the circuit, which is what we're doing with this solenoid. We're breaking the circuit and current flow that would normally go to this trim pump motor. And what happens when you do that is coils don't like to change current instantaneously. So what happens is the current flow through that coil slowly ramps off instead of stopping instantaneously. And what that causes is very high, or I guess depending on which way you want to look at it, low voltage spikes at these terminals, because it's trying to pull more electrons into that coil, and there's not any electrons to give here, so you basically get a really high or low negative voltage spike at this terminal. So I'm going to try this. If we don't see any sparks, which I'm not sure we will see yet, because I haven't tried this, if we don't see anything, then my backup plan here is I'm always looking for reasons to use this thing since I bought it. I'll hook up my oscilloscope probes to this and see if we can actually capture a negative voltage spike. But the first thing I'm going to do is get my camera set up here, and we'll see if we can see any sparking. And if we can, then we'll move forward into the next part, which is my idea on how to eliminate the sparking and potentially make these solenoids last for a much longer time. So let me get my camera set up here and see what we can find. Be right back. Alright guys, tried to get you in there as close as I could, if anything so you can see it, but also so I can see it on video footage if it's not clear. So alright, double check, everything looks okay, so here goes. Oh yeah, there's some definite sparking going on there. So that kind of proves my theory is these things are not going to last that long with that kind of sparking going on. In industrial contactors and things like that are used for motor starting, and that's why motor starters are such big beefy pieces of equipment. When you see a motor starter, a magnetic motor starter, they're usually these huge contactors that you'd be like, oh, this thing must be for some 100 horsepower industrial motor, but you'd be surprised you look at it, it's 3 or 4 horsepower. They're heavy duty pieces of equipment. I mean, there's a lot of spring pressure that goes in there, and the key to eliminating arcing is to make and break that contact as quickly as you can. Because what's going on there is when we get that high voltage spike in there, you're actually what's the word here? I forget. Basically, you're turning the gas in between those two contacts into plasma, which is a very conductive path. Because that high voltage spike allows that current to jump across that gap, which it normally wouldn't be able to do it. In this case, 17 volts or 18 volts. And that gap, the longer it takes to separate those two contacts, the longer that arc lasts and the more damage it does. So in industrial equipment, well, for one, AC is worlds better than DC. AC, whether you live in US or Europe or wherever, is either at 60 hertz or 50 hertz. So 60 times a second or 50 times a second, that voltage is at 0. Actually, 220 times a second. It's actually double, goes through 0 twice per cycle. So that arc can only last that long because the voltage will cross 0 and then there's no current flowing. But DC doesn't have that situation, so it's going to flow as long as it can jump that gap. So a couple of ways to alleviate that are through RC snubber networks, which is literally that. RC is resistor and capacitor, but there's some knowledge involved there in having to size the components. But what I want to try here is actually using a flyback diode or a freewheeling diode. A lot of times they're actually used on relays like this, actually, between the coil terminals, because this coil is, again, basically the same thing as that motor, just much smaller. So this coil is doing the same thing. You're getting voltage spikes at those terminals every time this opens and closes, but they're not nearly as big of a issue because the current in this coil is so small. That being said, I want to see if I can test this where I will hook up a diode from the terminal that is getting that high negative voltage to ground. And basically, you know what? Let me draw this out on paper so maybe it'll make some more sense. Be right back. Alright, hopefully you can see this. So let me think about this. What we have now is a battery going to a motor, which I'm going to draw as a coil again, because that's essentially what it is here, back to the battery. Pretty simple circuit. So the issue here is, let's I actually posted a picture on this in my Iboats thread on my restoration, asking if people thought this was a good idea. Anyway, so let's draw that as a switch. I'll draw it over here again so we can show the different cases. And one more. Okay, so in our initial case here, we have a battery, the motor, call that a motor, battery, motor, and a switch. Switch in this case would be your solenoid, but regardless. So in this case, when the switch is open, nothing's going on. There's no way for current to flow, it's just kind of sitting there. Then what happens is when you close the switch or your solenoid, you're going to have current flowing through the switch, through the coil, out the coil, back the wire, and back into the battery. So that's your conventional current flow, from positive through the motor back to negative. And if you remember what I said earlier, when we open this switch, the instant we open the switch, the current in this coil is going to try and continue to flow, but since this is open, what you get is a big buildup of electrons here, because it's trying to draw current through this, but there's no source of electrons. So you get this really big negative voltage spike. So for example, you might get negative 200 volts right here. And what that's doing is causing, let's blow up this situation here. That's your switch. You're getting big lightning strikes from there to there. So one way you can fix that is, let me draw this one more time. Is we can put a freewheeling diode like that. So this diode is reverse bias, meaning that current can flow towards the way the arrow points, but not the other way. Now obviously there's limitations to that. The diode I'm going to test here I think is good to 40 volts reverse bias. So as long as your battery or system voltage is below 40, it's not going to conduct. So what's going on here, if you think about it, is when that switch is closed, current is flowing through the coil as it normally would. It can't flow this way through the diode. So it's acting like it's not there. When the switch opens and you get this big, or when you would essentially get an excess of electrons here, a big negative voltage, what happens is that now has a path back. So as those electrons are flowing through this coil and they have nowhere to go, when you put this diode in here, now they have a path back. So what that does is minimize that negative voltage spike. Therefore, ideally saving these solenoids from these arcs, which will eventually damage them. So let's see if I'm making stuff up or if this actually works. Let me dig through my parts bin, find a diode that I think will work, and hook it up, and let's try it out. Be right back. Alright, got it hooked up here. You can see the diode that's running back to the negative on the battery, and then to the side that goes to the motor lead. Got the diode in the right orientation. Don't ask me how I know how. Alright, let's get the camera set up here. Maybe making you seasick. That should do it. And let's give this a try. Here we go. Here's the stuff blowing up in your face. Don't know about you guys, but I saw 0 sparks. That is awesome. So I'm going to take that as a partial win, and now I'm going to use the oscilloscope here to kind of verify and see what those voltage spikes actually are. Hopefully I don't fry my scope with the voltage spikes on the version without the diode, so let me give it a shot. Be right back. Alright guys, hopefully you can see that. I still have the setup here with the diode on. I'm going to see if I get any kind of a negative voltage spike here with the diode, see what it is, if it's there. A little more. Oh, there we go. Okay. So, it looks like it triggered when I pulled the solenoid open. Let's see if I can measure that, see what that negative voltage spike is. There we go. Okay. So I need to change to the horizontal. Okay. Let's see now. So that looks like I'm clamped my negative spike to around 8.7 volts, which is, that's pretty darn good. That's not going to jump anything. Cool. So right now when I open that solenoid with the diode, I'm getting negative 8.7, we'll call it negative 9 volts. So that's pretty good. So let me take this diode off and see what it looks like in the case where we were getting sparks. I'm going to pause this for a second while I take the diode out. 1 second. Alright, diode is off. Let's reset the scope here. So right now it's 0 volts. Let's change this to single shot. I'm going to lower my trigger down a little bit since that diode's gone. Alright, so what I decided to do here, which seems to be working, is I'm actually activating the single shot mode on the scope after I have the motor running, because there's just like so much commutator noise when I first start the motor that it's triggering the scope. So let's try it here and see if we can capture the negative spike when I open the solenoid. Here we go. There we go. Holy crap. So that is... wow. So it's going off the screen at negative 400 volts. That'll fry stuff. Jeez. Holy smokes, no wonder these things don't last. Alright, so without any kind of protection, you're getting over... well, I don't know, that's not a totally accurate comparison because I'm using a different motor. This one might be slightly worse, but I mean, that's... look at the difference there, negative 400 volts. And that's when it just clips off. I mean, it's obviously beyond that. Negative 400 volts without a diode, negative 8 volts or 9 volts with a diode. It's a no-brainer to me. I'm putting them on the new ones. Alright guys, hopefully you guys found that informational. I was actually pretty excited about that. That was pretty cool to kind of run that experiment and find out that it actually looks like it works. So yeah, I'm gonna put the diodes on my solenoids. Probably do it on the starter solenoid as well. I mean, in theory, it should have the same issue, same part. I actually posted my results of this on the Iboats forum, and everybody seemed to be kind of accepting of it. And one guy said he ordered like 100 parts or 100 diodes, and he's gonna share them with other people that might want them. So I thought that was pretty cool. Keep saying it. Thanks for checking this out, guys. I know I'm following up to a trim solenoid video. Like, what else could you possibly say about trim solenoids? But I took this cross section and ran this experiment and thought I'd share it with you guys. So again, thanks for checking it out, and hopefully you found it useful. Maybe you'll do this on your boat and see if you can get some extra life out of your trim solenoids, because God knows we spend enough money on these things. Alright, we'll catch you guys next time. See ya.